Hi and welcome to today's video. Today we are going to be talking about electrostatic potential energy and conservative forces. So if you like this video, do subscribe and share this video with your friends so that you guys can have a discussion with clarity amongst each other, as well as learn better and develop your thinking, right? So let's get started with today's video. So first things first, we'll be discussing about conservative forces and what is their relation with potential energy. Conservative forces form the foundation of potential energy, which means only for conservative forces is potential energy defined. That means if the force that is getting applied is not a conservative force, then there is no potential energy of that force, right? So we'll get to that point when we discuss potential energy. But what are conservative forces? Conservative forces are defined as forces which when applied in a loop, the final and the initial force at the final and initial point is the same. The force initially and finally are the same, right? For example, gravitational force is a kind of conservative force, right? Because we know that gravitational potential energy exists. Now, why is it a conservative force? Because if this A, the force at A will be equal to force at C, but so because the gravitational force depends on height, so this say is x, then this is also x. Why? Because they are in the same line, and so there is no difference in the force over here. But as soon as I go down, this will become y. It will change to y because the distance has now changed, right? Inversely proportional. The gravitational force is inversely proportional to the square of distance. So it will change. But now C and D will have the same force again because they are on the same line, right? But again, when we go back from D to A, the final force is again x at point A. The final force at point A, which is also the final point in the closed loop, is the same as the initial force on point A, right? So that becomes the definition. Now there are certain forces like spring force, like gravitational force, like Coulomb's force. All of these forces are conservative in nature, right? That means they depend on the distance and different other aspects, but in a closed loop, when I take a particle and run it through a closed loop, the force in the at the initial point and after the closed loop running is the same. That is how we define a conservative force, right? Why is this so important? It is so important because when we now look at potential energy, we're talking about general potential energy right now. We'll come to electrical potential energy in just a moment. But first, let's understand what potential energy is. Potential energy is the energy that gets stored in the object by the virtue of its position, right? By the virtue of its position. So, if I'm taking the same diagram, if my object is going through this loop, if my force is getting pushing this object over there to point B, I take it slowly. So what I'm assuming is that there is some work done by this force slowly without accelerating the object to get it to point B. Why is this so important? Again, because if the particle gets accelerated, it will lose energy, because every accelerated particle starts losing energy. So what we are saying is, if I slowly take this particle without accelerating it, but with applying that force available to us, we are moving it in this direction towards B, what is happening is this length, say this is length L, the work done by the force along this length L gets stored in the object as it reaches point B. Okay, so this is how it will be. But now remember, this is the work, the potential energy that is stored is by this force F, but not by the gravitational force applied. Gravitational force is perpendicular to this direction downwards. So only the force that is applied here to move it from A to B are we talking about that. This is the only energy that gets stored, right? So by the virtue of its position from A to B is the force getting stored in it, right? The energy getting stored in it, my bad. Now, again, it does not really work if there is no opposing force. There needs to be an opposing force as well. That means if F is just moving from here to there, it might add up, but if F is moving against some another force, say F dash, which is equal in magnitude but opposite in direction, now the potential energy gets stored properly. Okay, now this is how we define it getting stored. So potential energy is essentially the work done against a force, be it the gravitational force or electrical force or whatever force, against a conservative force which gets stored in the object by the virtue of its position. Let me give you an example very quickly. If I take this pen, right now it's here, say the potential over here is x. Now when I lift it to a height h, what's going to happen is I have done some work through my hand, opposing the gravitational pull on this pen, and I am slowly lifting it without accelerating it upwards to a height h, which means I have this work done along the height h by my hand has now gotten stored in this pen because it went from here to here because of the virtue of its position. So it gets stored in that object, but again it is opposite, the work done opposite to a conservative force which gets stored, right? Once we understand this concept, now electrical potential energy becomes easy. Electrical potential energy is quite simple to understand once we have the basics right. Electrical potential energy, if I have a charge capital Q, this is the source charge, and I have a charge small q like this, and I want to take this Q from R to P. Now, why am I taking it from R to P? Because the force on Q due to capital Q is repulsive. That means this charge wants that Q to go away. So when I bring the charge from R to P, I have to bring it with an external force. That means I have to use my hand to pull it slowly to get it to point B. And when I'm doing the work against a force, a conservative force, which here is the Coulomb's force, I am storing that energy in this particle Q. Okay, so suppose if the potential energy over here at R is say UR, and the potential energy here is UP, then the potential energy that was applied by me or that got stored in Q will be equals to delta W, which is simply equals to UP, which is the final work minus initial, and this will give me my work done or the change in potential energy of this charge small q. Okay, very important to simply understand, right? So this is what potential energy is about. Now when we are talking about a test charge, right, so another important thing over here is that potential energy only works when we are talking about a difference. Why? Because potential energy of P does not matter to me if I do not have any comparison, right? If I can't compare it with anything, then if UP is the potential energy of P at point P, then what do I do with it, right? But the moment I have a comparison, okay, oh, I have another point R, and compared to R, P has a greater potential energy, that means something. And how much is the difference? This is the difference, right? Therefore, potential energy is always mentioned and taken as a difference. Now, when we take it as a difference, how do we then define potential energy for a point, for a single point? That means, how can I define P, the potential energy at P? What I do is, I use convention. Convention is just agreed upon rules by this community. Okay, so the community of scientists came together, they decide that, hey, let's choose this, let's agree to this form, and then everywhere we use it, we can use this convention. So convention is just an agreed upon rule, right? It's not a nature's rule, it's just an agreed upon rule. So by convention, what we do is, we take potential energy of infinity. So an infinite, a point at infinity from this source charge has a potential energy of 0. So we take that as 0. We take U infinity as 0. So now what are we doing is, when we are talking about a single point, potential energy of a single point P, what we are now saying is that we have brought the charge, the test charge Q from infinity, where it was 0, and we've slowly pulled it to get it to point P, and that is the potential energy that is getting stored in Q at point P. Okay, so delta U is equals to UP minus U infinity, which gives me UP. This is how we get the potential energy for a single point, or this is how we define a potential energy at a single point, right? Important to understand, very important to understand, because this is where a lot of people and students make mistakes, right? So that's it for this video, and I'll cover the question, the formulae in the next one. Awesome. So I hope you like this video. If you did, please do like, subscribe, and put that notification bell to use, so that you know when we are putting up the next videos, right? And to put in your suggestions, your comments in the box below, so that we know which topics you want us to cover next, and we'll get to that ASAP. Of course, if you have any doubts, do put it down in the comments below, and I'll get to it as soon as possible. Right? See you until next video.